Welcome everybody to another geometry lesson. Today is going to be our last lesson of Unit 6. It went by so quickly. Lesson 6.5. Inequalities in 1 and 2 triangles. This lesson has a lot of definitions and a lot of problems. But here's the thing. The concepts taught by it are really quick and short. So this is almost like a grab bag of a section, where you're going to get a bunch of different types of problems that won't take very long each time. Let's start at the bottom of the first page. Down here, we have a task. Draw an obtuse scalene triangle to the right. Mark the largest side and angle with a star. Mark the smallest side and angle with an X. We want to see what we notice. So, obtuse scalene. That means we've got to have a pretty big angle here, like so, and all three sides cannot be the same length. So this is a suitable obtuse scalene triangle. Which one of these is the largest side? Well, it definitely looks like this one is going to be our largest side, so I'm going to mark it with a star and color it in. The largest angle is the obtuse angle for sure. Like, look at how small these acute angles are. So there is the smallest or largest angle. I made the smallest side, this one down here, so I'm going to mark that with an X. It's sort of tough to tell which one's the smaller angle, though. You can use a protractor if you'd like, but I think that just by the way I drew this triangle, this angle up here is barely smaller than this angle down here. So what do we notice? Well, if we look at the largest side and the largest angle, they're across from each other. They're not touching, they're across the way. But the same goes for the smallest side and smallest angle. This is the core of what this unit is all about. The triangle longer side theorem and the triangle larger angle theorem. It goes like this. If you have a triangle with three different sides, three different angles on it, the largest side is going to be across from the largest angle, like so. Any other side that's smaller is also going to have a smaller angle. So if I told you that this side was 15, this angle is going to be smaller. Let's say it's like 45 degrees. I don't think that's accurate, but it's around an approximation. So the triangle longer side theorem basically says if you have a long side of a triangle and a smaller side of the triangle, the angle across from the longer side is bigger than the angle across from the smaller one. Let's write it out. If one side of a triangle is longer than another, then we can conclude the angle opposite the longer side is bigger than the one opposite the shorter side. Perfect. So this theorem helps us compare different angles. If you have the side lengths, you can compare the angle measures. So what do you think the triangle larger angle theorem is going to say? It's basically going to be the converse. It's not exactly the converse, but it might as well be. This one says, If one angle of a triangle, I'll use that 45-degree again, is bigger than another angle of the triangle, let's call this one, let's call it 30 degrees. This isn't going to be the same triangle, just because this math obviously wouldn't work out. But if we have an angle that's larger than another one, the side across from the large angle has to be bigger than the side across from the smaller angle. And it looks like that's true. We'll say that this side is, I don't know, 100, and this side is 20. So the triangle larger angle theorem says if one angle of a triangle is larger than another, then the side opposite the larger angle is longer than the side opposite the smaller angle. We can use this in a bunch of different ways. So let's take a look at examples 1 and 2. Both of these involve us listing things. A is having us list the angles in order, and exercise 2 has the sides listed in order. So let's take a look. In part A, the longest side is 32 feet. Since that's the longest side, it means that K, opposite it, is the largest angle. So I'm going to say angle K is bigger than, we use the greater than symbol for this. It's going to get confusing with the angle symbols too, I know. The second largest side is 26 feet, so J is the second largest angle. K is bigger than J, and since the smallest side is 24 feet, the angle opposite it is angle L. Angle L is the shortest side, or shortest angle. Perfect. That's our final answer, believe it or not. Angle K is greater than angle J, which is greater than angle L. Let's take a look at the next one in exercise 2. In exercise 2A, it's asking us to list the sides of each triangle this time. But it's the same thing. We're going to have a largest side, a middle side, and a small side. Well, the largest angle is going to be across from the largest side. So that 112 is across from line segment XZ. So, of course, that means we have to say that XZ is the largest. Actually, you wouldn't need the line segment symbol above, I apologize, because we're talking about the measure of the side, not the side itself. Next up, the next largest angle is going to be this one right here, angle X. So the side opposite angle X, YZ, is the next largest. By process of elimination, since 32 degrees is the smallest angle, YX is the smallest side. I'd like you to try out both part B's of these problems. So pause the video and come back when you're done. How did we do? If we take a look here in part B, it's sort of the same thing as part A, really. We're comparing the longest side to the largest angle, 28 and L. Second largest side is 25, so K is the second largest angle. 13 is the smallest, so J is the smallest. But in part B here, I gave you a curveball because I didn't give you all of the angle measures. But we should know by now that a right angle is 90, which is definitely bigger than 33 at least. And to complete the triangle, since all triangles add to 180, this one has to be 57. No, sorry, 47. Did I do that right? No, it is 57. Okay. So this one is the second largest, and 33 is the smallest. That means DG, which is opposite the right angle, is the longest. GF, which is opposite this 57 degrees, is the second. And across from the 33 degrees, FD is the smallest. Perfect. Next up on our list, we have something called the triangle inequality theorem. Now, this one involves us asking some pretty theoretical questions here. In class, we're going to do a brief activity with this, but I want to ask you all, is it possible to have a triangle with one side that's 100 feet, 1 foot, and 3 feet? Well, let's try it out. We know that one side of this triangle is going to be really, really long. The 1 foot side of the triangle is going to be really short, and the 3 foot side of this triangle is going to be really short. These two ends don't meet up at all. They're not long enough. So it's possible to actually have some triangles that can't exist. The ends just don't meet up. So we need a theorem that'll tell us what types of triangles do exist and what types of triangles do not exist. Here is the general rule put out to us by the triangle inequality theorem. Get ready. The sum, so we're adding together, the sum of two lengths of a triangle must be greater than the length of the third side. What that means is, if you want to build a triangle, you've got 3 sides. The 2 smallest sides added together have to actually be bigger than the longest side. So let's take a look at our paper again here. 1 plus 3 is 4, and since 4 is not greater than 100, that triangle could never exist. But what if I had a triangle that was 100 feet long? Let's say we had another one that was 36 feet long, another one was 64 feet long. This is a toughie. I'll make 100 feet, this length here. The problem is here. Is 100 less than 36 plus 64? I want to put this question mark over to show that we don't know. No, it's actually also not a triangle. The reason is 100 equals 36 plus 64. What that means is the length 36 plus the length 64 will exactly get to the end of this line segment, but that's not a triangle, that's just 3 lines on top of each other. The only way that this triangle will work is if the longest length is less than the 2 shorter ones added together. This one will work because 100 is less than 50 plus 75, 100 is less than 125. So we'll end up with a triangle that looks like this. Here's 100, 50, and 75. We'll have a correct triangle. That is the triangle inequality theorem. So let's get some practice with it in exercises 3 and 4. Exercise 3 basically tells us, decide if it's possible to make a triangle with the given lengths. Let's do A together. Here's how we do this. We always want the two smaller sides to be bigger than, or the sum of the two smaller sides to be bigger than the longest side. So step 1, find the longest side. 10 is the largest side here. So we need to see, is 4 plus 9 bigger than 10? I give that the check mark of approval, because 4 plus 9 is 13, which is bigger than 10. That means the triangle inequality theorem says this is possible. Pause the video and try out B and C. See if these ones are valid triangles. Hopefully you've had a second to analyze this. So here are the longest sides. I put them all at the right side so it's easier to look at. Is 5 plus 7 greater than 12? Unfortunately, it is exactly 12, so no, this is not a valid triangle. You'll end up with a line segment. For the last one, is 39 plus 26 greater than 68? Let's do the math. 39 plus 26, it's going to give us 65. Which is just short of 68. This is also not a triangle. The two smaller lengths just wouldn't quite be able to touch in this triangle. More commonly, you might be asked a problem like example 4. A triangle has one side of length 12 inches and another side of length 20 inches. Write an inequality to represent all possible lengths of the third side. Since all possible lengths are unknown for this problem, I'm going to call it x. And here's the problem. We want to see how small x is allowed to be. So here's if we say small x. And we want to see how large x can get. So let's start off by asking, if x was a small side, what's the smallest it'd be allowed to be? Well, if this is a small side, that means that we would have 12 and x as the two smaller sides, and it has to be greater than the longest side, 20. This is just an inequality we can solve. We can subtract 12 from both sides and get x has to be greater than 8. So we found a limit here. The smallest we can get is it has to be bigger than 8. We can do the same thing for the large side too. This time, what would your two small sides be? Well, if x is really big, bigger than these two, it means that 12 and 20 are both the small sides, and they have to be bigger than x when they're combined. 12 plus 20 is 32, so 32 has to be bigger than x. What we end up here with is a range of values. We know that 8 is our smallest, 32 is our largest, and we learned in Algebra 1 that we can always write this as a compound inequality. Since x is between 8 and 32, 8 is less than x, which is less than 32. Our triangle can have any of these lengths in between. Very nice. Let's take a look at the last couple definitions. We have a theorem called the hinge theorem, and it is not about dating sites. The hinge theorem is actually more commonly used than some of the other theories we talked about. The reason why it's called the hinge theorem is we want to think of it like a door hinge. A door hinge is what attaches the door to a wall and tells you how wide the door can open. So it can open up a little, or it can open up a lot. The hinge theorem, though, works when we're comparing two different triangles. Here's the specifics, y'all. Just like you're opening a door, the quote-unquote door has to be the same in both triangles. So one length of these triangles has to be congruent. But here's where the kicker is. We're going to have another length that is congruent to these triangles, but it's going to vary how wide this quote-unquote door opens. I'm going to mark down that this is the same as this length, but you see that these are two different angles, which means we're going to end up with two wildly different triangles. This triangle here almost looks like a right scalene triangle. This one over here almost looks like an obtuse scalene triangle. Here's the deal. We know that since this angle has to be bigger than this one, we'll call this 120 degrees, and we'll call this one 60 degrees. Since this angle is bigger than this angle, this side has to be bigger than this side. It's almost like what we learned before with the triangle, longer side, and larger angle theorem. The side across from the bigger angle is the bigger side. So this is 50 and this is 25. That's what the hinge theorem says. It sounds weird, but it just means that if you've got two triangles and you're comparing the two of them, when all else is equal, the third side across from the larger angle is bigger. It's going to be a wordy theorem, so bear with me. If two triangles have two congruent sides, and the included angle of the first triangle meaning the angle in between those two congruent sides is larger than the included angle of the second triangle, then the third side of the first is larger than the third side of the second. Bam. Very wordy, but it just means if you've got an angle that's opened up wider, the side opposite of it is going to be bigger when all else is equal. And of course, with every large theorem, there's got to be a converse so we can write just as many words, right? The converse as a reminder, just means that we flip it. So it also goes the other way. Let's say we know the following. We know that two triangles, once again, have two congruent sides. So I'm giving you that these two are the same and these two are the same. If we already know that the third side of one is larger, let's say this is 13 and this is 5, we know that this angle here is going to be larger than this angle here. We'll call this angle 1, this will be angle 2. We would say that angle 1 is larger than angle 2. So, let's write it all out. Here we go again. If two triangles have two congruent sides, just like the first, and the third side of the first is larger than the third side of the second. Whoops. So if one of their sides is larger, then the included angle of the first, again, that's the angle in between the two congruent sides, is larger than the included angle of the second. Done and done. I feel like I burned calories writing out those definitions. Sorry they're so long, y'all. Let's see if we can apply it, though, because really that's what I'm most concerned about. Not if we can memorize it, but if we can use it. So here's exercise 5. We're told that ST and PR are two congruent line segments. We want to see how angle PST, which is going to be the angles from P to S to T, right here, compares to SPR. SPR is going to be this angle right here. They look congruent, but appearances can be deceiving. We want to figure out all we can using the hinge theorem. Here's the problem. The hinge theorem is contingent on us knowing that two sides of these triangles are congruent. We only have one congruency marking. The good news is, we do have a way of finding a second congruency. Look how PS and SP are on both triangles. That means that this is the segment that's congruent to each other. In other words, here are the two congruent segments for the first triangle, and they're congruent to these two segments on the second. All we have to do now is compare the two sides. So this side is 23, this side is 24. Since this side is 24, this is the larger side, it means that opposite it is the larger angle. Since 23 is the smaller side, only by a little, it means that this angle opposite it is the smaller angle. So we can say angle PST, which is the one down here, is larger than angle SPR. And just like that, that's it. That's the entire problem. Not as crazy as it looks, right? And that was a hard version, too. This is about the toughest version of this problem I could give you. exercise 6. We've got another long problem that talks about miles and directions. Let's read it out. Two groups of bikers leave the same camp, heading in opposite directions. Each group travels 2 miles, then changes directions, and travels 1.2 miles. Group A starts due east and turns 45 degrees towards north. Before we do anything, I'd like to draw us a quick compass rose here, just as a reminder. In a traditional compass, we point north up, east here, S south, W west. No eating sour watermelons. Then group B starts due west and turns 30 degrees south. And we have to figure out which group is further from camp. Let's draw this out. I'm going to represent the camp with a tent here. It's going to be a nice tent. It even has a zipper and everything. There we go. That's going to be my tent. It is not very good. Don't critique my art skills, please. I will cry. So there's our tent. Let's do 2 different colors for groups A and B. Group A starts due east for 2 miles, then turns 45 degrees north. So group A is going to go about 2 miles east, then turns 45 degrees, which we know is about this, towards the north direction. I'll label that as a 45-degree angle, and that's going to be 1.2 miles. It says they start by traveling 2, and then turn 1.2. Group B, we're going to use the color blue for, they don't start going east. They start going west 2 miles. So they're going to go boop, 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 boop. That's about the same length. That's going to be 2 miles here. But they only turn 30 degrees towards south. They're only going to turn slightly south. I'm going to say that's about 30 degrees south. Oops, sorry, I mislabeled, guys. I realize I gave the wrong label to this problem. That's where it can be a little bit deceiving. When we turned 45 degrees north, we turned 45 degrees north from the path we were traveling. This angle is 45. Similarly, in group B, we only turned 30 degrees from the path we were traveling. This angle is 30 degrees. There we go. That's why it can be a little deceiving. And we need to figure out exactly which group traveled further. To figure out which group traveled further, let's complete these as triangles. So here are their endpoints. We know that this distance is the distance for this group. This is the distance for this group. From our diagram, it looks like group B traveled a little further, but we have to prove it. So we're really dealing with these triangles here. Let's start with group B's triangle, just because it's on the left. On group B's triangle, we don't have any markings, but we do know this. If this angle here is 30 degrees, what's this top angle here? Well, it's supplementary. It needs to make 180 total, so it's got to be 150. Similarly, on the red side of things, oh, I'm so sorry, this is very messy. This angle is 45 degrees, so what's supplementary with 145, or with 45? 135 degrees. It turns out that group B is across from the bigger angle, the 150 degree angle. And group A is across from the smaller. That means that group B is further from the camp. Group B is further from camp. There we go. Thank you so much, everybody. Hope you enjoyed this lesson. Have a fantastic rest of your night. Good camping!